So the next is the addition rule, or the addition theorem. It helps us to find probabilities of unions of random events. So for two events, probability of union of A and B is sum of probabilities minus probability of intersection. So P of A plus P of B minus P of A intersection B. This can be easily proved if you interpret probability as an area. So if you describe these events, A and B, as circles with some intersection, not empty intersection, so using Euler Venn diagrams, you will see that area of the union of A and B can be found according to this formula. So if you add just area of A to the area of B, the area of intersection will be counted twice. And to count it just one time, you should subtract area of the intersection. So the same thing we see here. For three events, we have P of A union B union C is equal to sum of their single probabilities minus probabilities of double intersection plus probability of the triple intersection. So this can be explained with the same diagram. So if you draw a diagram with three intersected circles, you will see that this is true. And the last formula we will deal with while finding probabilities of complex events is the probability of the complement event. This formula is very simple and it's just obvious. So probability of not A is 1 minus probability of A. As you know that as a result of our experiment, at least one of two must occur, either A or not A, so sum of their probabilities must be equal to 1. And that is why this equality is true. Another example. Let's say that somebody has stolen somebody else's bank card and is trying to guess an unknown PIN code. PIN code consists of 4 digits. What is the probability that 2 attempts will be enough for him to guess a 4-digit PIN code? So the first step is to introduce properly the notation. So we are to denote some random events connected with this experiment with the respective letters. So let me say that A1 is probability that the first attempt is successful. So probability that he enters the correct PIN code just from the first attempt, from the first time. So, and A2 is the second attempt is successful. So my event of interest is that 2 attempts will be enough to guess this PIN code. So how I can express my event of interest with these two, A1 and A2. Let my event of interest be B. So B is 2 attempts are enough. So B means either the first attempt is successful, so A1, or means union, or the second attempt is successful, someone may say, but so the second attempt will take place only in case when the first attempt was not successful. So the second attempt takes place only after unsuccessful first attempt. So A1 or not A1 and A2. So the first attempt is successful, or the first attempt is not successful and the second one is successful. So that is how my event can be expressed with the help of A1 and A2. So now let's apply the formulas we already know. So P of B is P of A1 union not A1 and intersection A2. So the first step is to apply the addition rule here. According to the addition rule, this is P of A1. So I have union of two events. This is the first one and this is the second one. So plus probability of the second one, not A1 intersection A2, minus probability of the intersection of the first one and the second one. So intersection of A1, not A1 and A2. But now I see that this event is an impossible one. So here I see A1 intersection A2. So both are to take place, both are to occur, A1 and not A1. This is impossible. So this event is an impossible event, and that is why its probability is 0. Probability of an impossible event is 0. So and here I can apply the multiplication rule. So here I have P of A1 plus, and according to the multiplication rule, this is P of not A1 times P of A2 given not A1. So, and now let's find these three probabilities we have in this expression. So P of A1 is a probability to guess the 4-digit PIN code from the first attempt. So how many 4-digit numbers we have? 10,000. Let's say that 4 zeros is also an acceptable PIN code. So from 4 zeros to 4 nines, we have 10,000 choices. And only one is correct. So only one PIN code is correct. So probability is 1 over 10,000. Then P of not A1. We can say that from the one hand it is 1 minus probability of A1. So 1 minus 1 over 10,000, that is 9999 over 10,000. Or we can say that this is a number of outcomes favorable for this event, and all outcomes are favorable except for the one correct pin code, divided by the total number of outcomes, that gives us the same result. So 9999 divided by 0, 1, 0, 0, 0, 0. So this is probability of not A1. And then probability of A2 given not A1. So P of A2 given not A1. Probability that the second attempt will be successful if we already know that the first was unsuccessful. So the first attempt has already taken place and it was unsuccessful. So we know that one combination of digits is wrong. So total number of choices for us is not 10,000, but 9,999. So as we know that one combination is wrong. So that is why here in denominator we have 9999. And in numerator we have still 1, because still just one pin code is a correct one. So after having these three probabilities, we substitute them to this formula, and what do we get? 1 over 10,000 plus 9,999 over 10,000 times 1 over 9999. This is cancelled, and here we have 1 over 10,000 plus 1 over 10,000. That is 2 over 10,000. So 2 attempts, 10,000 choices. Probability is 2 over 10,000. Actually, we can get this answer just by our intuition, but still, this example also shows us how can we apply the formulas we have just discussed. So here we used the addition formula, the multiplication formula, and the formula for the probability of the complement event. Another example. We have a system of 2 elements united in this way. So that means that system is working, is in service, if at least one of these 2 elements is working. That may be 2 elements of an electric chain, or 2 cash desks at a shop, so that shop is working if at least one of 2 cash desks is at service, and so on. It doesn't matter. And so the main thing is that the system is working if at least one of the 2 elements is working. At a random moment of time, first element is out of service with probability 0.1, and the second one is out of service with probability 0.2. And these 2 elements are independent. So the state of the first one is independent of the second one, and vice versa. So they are in service or out of service independently from each other. So let me say that elements are independent. We know that now the system is working. What is the probability that the first element is out of service? So the system is working now. What is the probability that the first element is out of service? The first step is notation. So I am to introduce some letters to denote events we will deal with here. Let me say so. Let me say that A is that the first element is in service. B, the second element is in service. And C is that the system is in service. So how can I write down the thing I'm asked to find here using these letters? So they say the system is working. That means that something has already happened. So some event has already happened, and we are to find a conditional probability. So event C has already happened. So we are to find probability of something given C. And probability of what? They ask, what is the probability that the first element is out of service? And event A is that the first element is in service. So first element being out of service is not A bar. So this is the probability we are asked to find here. P of not A given C. But actually, one may say that we don't need letter C here. And he will be right, because we are told that the system is working if at least one of two elements is in service. So that means that C is equal to A union B. So A union B means at least one of two events occurred. That is why we can just replace C with A union B. And now we are to apply the formulas we already know. So let's do this. The first is the formula for the conditional probability. So I have probability of one event given another one. According to the conditional probability formula, this is probability of intersection of these two events namely not A and A union B divided by the probability of the second one, of the A union B. So now I open the brackets here in this expression and I get P of not A intersection A union not A intersection B. Union and intersection are like addition and multiplication here. So the general rules for opening the brackets as for addition and multiplication can be applied. And in denominator, I still have P of A union B. So here, this is an impossible event. A intersection not A. This is an impossible event because A and not A cannot happen at the same time. And as we know, union of an impossible event and any other event is equal to this other event. So here in this expression, only this not A intersection B is left. So this simply disappears because this is an impossible event. And now we have P of not A intersection B in numerator. And as for denominator, I'll apply the addition rule. Probability of A union B is probability of A plus probability of B minus probability of A intersection B. And the last step is to say that they told us that elements are independent. So they are in service or out of service independently, one from the other. And that means that events A and B are independent events. And for independent events, probability of intersection is equal to the product of probabilities. So I can replace this P of A intersection B with P of A times P of B, and P of not A intersection B with P of not A times P of B. So if events A and B are independent, then not A and not B, not A and B, A and not B, all these four pairs are independent also. So here I have P of A plus P of B minus P of A times P of B. And here I have P of not A times P of B. And so they told us that probability that the first element is out of service is 0.1. This is probability of not A. 0.1 is probability of not A, and 0.2 is probability of not B. So probability of not A is 0.1. That means that probability of A is 0.9. Probability of not B is 0.2. Then probability of B is 0.8. And so now we substitute these numbers to this formula. And we have 0.1 times 0.8 divided by 0.9 plus 0.8 minus 0.9 times 0.8. And this is approximately equal to 0.0816. So you can see that unconditional probability that the first element is out of service is 0.1, and conditional probability when we know that the system is working, that the system is in service, is a little bit less than 0.1. Why? Because this additional knowledge that the system is in service excludes the situation when both elements are out of service. both the first and the second. As this situation is excluded, then chances for the first element being out of service are a little bit less than in situation when we don't know this information.